Hello everyone and welcome back to the second video of my constructive anatomy class. In the last lesson we talked about some of the terms we use when we talk about linear perspective and what those mean. In this video we're going to go a little bit deeper into the technical aspects of perspective and learn all about the construction of the fundamental forms in proper perspective. Now fair warning, this is going to be a rather information heavy video, as we're going to aim for as perfect perspective as we can get of these fundamental forms. Like I said before, this can't be a full course in perspective, though I do recommend that to any student. You can see from this incredible Leonardo da Vinci drawing just how much power a full knowledge of perspective can give you in creating artwork. For some of you, this video will feel a little bit overwhelming, as it's packed with tons of information about the construction of these basic forms. But for now, don't get overwhelmed. One of the advantages of video courses is you can go away, have a break, and come back refreshed, tackling these topics at your own leisure. Also, while I do recommend that you have a few goes at tackling perspective in this very technical way, for the large part, most of the exercises I will expect you to draw in a freehand perspective or a sort of guesstimation of proper perspective, as there will be too many moving parts for you to properly plot absolutely every form. And it's really very valuable for you to be able to draw in an intuitive way as well as this more technical way. The reason we study it in such a technical way is to get it into our subconscious, so that we can use it to express ourselves in our artwork. And this must never be forgotten. The technical must never overcome the expressive, as this is the primary reason why we create artwork in the first place. In this particular type of drawing, we will not be guessing anything, and this is the main point. Once we have decided the space that our picture exists in, nothing should be guessed. All units should be worked out from other units. Now, without any further ado, let's move on to our first perspective construction. Here we start, as we always do, with a blank page that we've drawn a horizontal horizon line on. The first thing we add are our diagonal vanishing points and our center of vision. Again, deciding how far away our viewer is from the page. The next thing we do is find our 30-degree vanishing point and our 15-degree vanishing point. Again, expanding these into cones of vision, as these are going to be useful in our perspective construction moving forward and avoiding distortion. Now that we have our perspective grid all set up, we can get into our first construction. Our first construction today is going to be the one-point perspective cube. So called because it has one vanishing point. The cube is going to be our most fundamental form, as it is a 1 by 1 by 1 dimension solid. It's going to form the basis of how we measure everything in perspective. So it's very important that we understand this form properly. So as we get into the construction, the first thing that we need to decide is where exactly our cube is going to be in our picture space. Just as we talked about before, we're going to try to keep it within the 60-degree cone of vision to avoid distortion. I'll place it right here. Now this is the only part of the construction that is actually guessed. Now we've decided where this line is placed and its height. Everything else about the cube has been decided already. We have to just trace the lines. Now, as the front plane is perpendicular to our vision, there isn't any convergence happening top to bottom or left to right. This means we can draw this same length left to right and top to bottom to create a square. From this square that we've drawn on the flat, we can project back to our vanishing point, in this case, the center of vision. This is why it's called a one-point cube, as there is only one vanishing point that it disappears to. But now we run into a problem. How do we know how far back to go? At the moment we know this distance is going to be shorter than our initial line, as it's foreshortening back to the central vanishing point, but we don't know exactly how long it's going to be. Lucky for us, there's a way to work that out. One of the things we know about squares is that if we cut them in half, we're given a line at 45 degrees. So if we trace a line back from one of the close points to the 45-degree vanishing point, where it intersects with the line going back to the vanishing point, is going to be our distance back for our cube. We can then use this intersecting point, expanding out and drawing lines for all of the remaining lines of the cube. At this point, you may notice that I'm ignoring the overlap rule at this stage in the drawing, almost drawing the cube as though it's made of glass and I can see through it to the back lines. This is a very important point in how we're going to approach drawing in this way. It is important that you understand how to perceive the unseen side of an object. So as we move forward, I want you to, as much as you can, draw in this X-ray manner in the early stages of the drawing. Now that all of this is done, the only thing left to do is finish the drawing by erasing all of our unnecessary lines and apply our line weights in accordance to the principle we spoke about in the last video. And there we have it, the 1-point cube. Now that's done, let's put that to one side and move back to our original perspective grid to get ourselves ready for the next construction of the 2-point cube. Once that's done, the first thing we need to decide is the placement of our cube and what orientation we want it to be on the page. For this cube, I've decided to do a 45° by 45° cube, but you could choose any angles. They just need to be 90 degrees apart. As you can see, I projected my lines back to the vanishing point of the angle I want for the cube. In this case, 45° by 45°. Now we're presented with that same problem a little bit earlier. How far back do we go to make sure that we've got a 1x1 cube? Lucky for us, there's a solution here. What we're going to do is take our line out to both sides and then take them back into space onto the lines that we projected to our vanishing points. The first stage of this is to take our length horizontally out from our initial line, as you can see here. The next thing we need to do is find what measuring point is going to project those lines into the same proportion on the horizon line. So the next thing we need to do is project a line down to the 45° vanishing point. Once we have that, we need to take a line from each of the 45° vanishing points and transfer those onto the horizon line, as you can see in the diagram here. This will give us our first measuring point, which we're going to label MP1. We can then do the same for the other side, giving us our second measuring point, or MP2. Once we have these, we can trace lines back to them, and where they intersect with the original lines gives us the distance it goes back before we get our next vertical in our cube. Once we have that, we can logically work back every other line of the cube, giving us a perfect 1x1x1 cube in 2-point perspective. After that's done, the only thing to do is to finish it off, like so. Now the next construction we need to learn for the cube would be a 3-point cube where each axis is disappearing off to a vanishing point. But that's the most complex construction we're going to discuss today, so I'm going to leave that till the end. So with that said, we're going to move right along onto the construction of the cylinder. Now, to construct the cylinder, there's a little bit of groundwork we need to do about the construction of a circle in perspective. Pictured at the top is a generic construction for the circle that we can project into space, as you can see on the bottom. This comes from Loomis and it is very effective. However, in using this construction, there is always a certain amount of guesswork involved. And since we're working in a very technical way today, I don't want to leave it at that level of guesswork. So we're going to look at a slightly more advanced construction of a circle that I think everyone should do a few times in their artistic life. Now, as you can see, this construction has some very simple steps. First, we start with a square. We then divide that square into quarters, and here's where Loomis ends the construction by adding the circle. However, what we're going to do is we're going to continue that vein and divide the square further into 16ths. For the next stage, we're going to go out from each of the corners of our square to the first row of our box, placing a point where it first intersects our grid. Following this up by doing that all around the square. Now, if you followed that right, and including all of the halfway points of the square, you should be left with 12 points on your square. Now, the great thing about this construction is all of these points are precisely placed on the circle, as you can see here. This means that if we plot this in perspective, we get an exact set of points that show us where to place our circle in perspective. Another idea that I need you to grasp is that no matter what constructions we use, a circle projected into space is always going to take on the form of what we know as an ellipse, seen here in this diagram. Now, what an ellipse is really just a squashed circle. As you can see here, as the ellipse turns away from us, it gets gradually more and more squashed till it ends up a line in the last step. This will always be the shape that a circle takes on when it is projected back into space. Another aspect of an ellipse important to understand is that they are always perfectly symmetrical in the two-dimensional sense. Each ellipse have in common what we call a short axis and a long axis of the ellipse. So called because the long axis is the axis of the ellipse that is not subject to any foreshortening, so it stays the same length no matter how squashed the ellipse gets. The short axis, on the other hand, takes the brunt of the foreshortening and gets shorter and shorter down to when it becomes nothing at the end. The reason it's really important to understand the short and long axis of an ellipse is because they control the perceived angle of that ellipse on a form. To show you what I mean, let's have a look at a cylinder with an ellipse rounding it out at the top and bottom. As you can see from this diagram, the short axis of the ellipse is in line with the central axis of the cylinder, and this looks like a properly balanced cylinder. And this is something you can remember that will always be true of cylinders. The short axis of an ellipse will always be in line with the central axis of the form it is perpendicular to. To show you how changing this axis changes the perception of the ellipse, let's have a look at a drawing where I have it slightly different. Here the short axis of the ellipse is not in line with the central axis of the cylinder, and we can see that this gives the appearance of a more slanted cylinder, as if I had diagonally sliced my initial cylinder. Another important fact that we need to understand about ellipses is best seen when we look at a very large ellipse and break it down, already marked out. Now if we draw a square plane around this ellipse, and then we find the true center of this ellipse by drawing the diagonals of this box, we can see that the perspective center of this box is not the same as the center of our short and long axis. In fact, in general, the true center of the ellipse is not going to line up with the short and long axis of the ellipse. To understand a little better why this happens, let's take a look at our observer, again being looked at from the top down. This time he's looking through the picture plane at a big flat circle. Now I've had to make the circle a lot bigger in this case to exaggerate the effect, as it is really quite subtle. Now if we drew a true halfway for this circle, it would look something like this. And if we take the points where the circle is widest at that center and trace them back to our observer, we get something like this. However, this is clearly not the widest point that the observer sees. If we have a look at where the observer's eye line is tangent to the circle, i.e. where he would stop seeing the circle, it actually occurs down here. You can see that this creates a wider width on the picture plane than the actual center of the circle. Because of this, this line would actually be the long axis of the ellipse, counterintuitively. To make this a little bit more clear, let's do what we did last time and project these points out into perspective space so we can see what our observer sees. It might look a little bit something like this. Now, because the circle is far bigger to explain the effect more clearly, you wouldn't really see this much of a difference in an undistorted perspective. But it does give you the idea that these are not the same thing. And the actual center of the ellipse is always going to be in the far half of the ellipse. Now that that's out of the way, let's talk about how we would actually go about constructing a cylinder. Since we already know how to construct a box, we're going to skip those stages and start with a 2-point box already worked out within our grid. The next stage will be to begin breaking down the plane that we want to turn into an ellipse into quarters. After that, we'll perform the next stage where we turn that into sixteenths. From those sixteenths, we find 2 of our points and then the rest of our points. And now we have enough points to properly plot out our ellipse, as you can see here. Once we've done that, we move on to the second plane that we want to turn into an ellipse, repeating the same process to get a new set of points to create our second ellipse, like so. Once we have those 2 ellipses, it's really just a case of joining up our cross sections and then erasing our box, and finally erasing all of our unnecessary lines to get that final finish, like so. Luckily for us, the next construction is going to be quite a simple one, as the cone starts very much exactly like the cylinder. So the first half of the cylinder construction is going to equally apply to the cone. The only thing that is different is that instead of plotting the second ellipse, we are going to draw lines straight down to that central point on the far plane. We can do this because a cone is basically just a cylinder with a squashed top. After that, we can erase our box and finally erase all of the lines for that finish. The sphere has a slightly more involved construction that can sometimes be a little bit confusing to students. The first thing that we need to do is plot all our halfway points on each of the 3 axes. Here seen in 3 different colors: red for the z-axis, cyan for the x-axis, and magenta for the y-axis. Once we have these halfway points marked, the next stage is going to be to pick one of these halfway planes to plot an ellipse in, which will go about in exactly the same way we have for the cylinder, plotting out our points and then dropping in an ellipse. Once we've done this for one axis, it's simply a matter of repeating the same steps for the other 2 axes. Once we have all of our ellipses planned out, we merely need to connect all of these various cross sections with a circle, as a sphere is a circle from any point of view. With that done, we can erase our box and then finally erase all the unnecessary details to leave us with our final finish. Now that we understand how to construct the sphere, let's strip back to our original perspective grid so that we can tackle our final and most complex construction, the 3-point cube. What makes the 3-point cube so complex is that it is receding in all 3 axes. And so far, we've only learned how to turn the cube in one axis, that is left to right. However, since the cube is now going to be tilting up and away from us, we need to talk a little bit about what happens when parallel lines tilt vertically up, like so. These set of parallel lines are going 45 degrees upwards, and as such are going to line up on this vertical axis coming out of the center of vision. This creates what we're going to call a false horizon, and any degree of turn from these parallel lines to the left or right will disappear to a point along this false horizon, as opposed to the true horizon. Any lines tilted up 45 degrees will lie somewhere on this false horizon. However, we come to a problem again. We don't know where on this new false horizon the different angles are going to disappear. Now, a lot of artists and a lot of art books teach that you can merely project each angle up vertically and use that for the new angle on the false horizon. Now, this will work, and it's a good shortcut when you want to get some perspective done quickly. However, it's not strictly true, and I can show that to you. If I turn these parallel lines into a square plane using the exact same method that I did for the 2-point perspective cube, that is projecting the line back to the 45-degree cone of vision, transferring that line down to from the vertical line this time to create a measuring point, and then tracing back to that measuring point to give me my perfectly square plane, I can use this square plane to find my 45-degree vanishing points on the new false horizon. And as you can see, they are not vertically aligned with the true horizon's vanishing points. Now that we've got our new vanishing points sorted out, it's time for us to decide where our 3-point cube is going to land. For this 3-point cube, I've decided to do a 45 degree by 45 degree by 45 degree 3-point cube. So as you can see, it disappears off to the 3 45-degree vanishing points. Now we run into the same problem that we ran into with the 2-point cube again, but this time we don't even have one side to rely on. So we're going to have to draw lines in the flat and then project them back into space to get our proportionate cube. In the same way we got the tilted square cube, we're going to find our first line of our 3-point cube by transferring the line to the vertical axis and tracing the line back to the vanishing point. We discover our first vertical line of our 3-point cube. Repeating this process for the 2 vertical lines on the new false horizon for both sides, and then tracing it back, we find our 2 vertical distances. Since we now have all of the distances sorted out on our 3-point cube, it's really just a matter of tracing the last few lines back to their vanishing points. And once we have that, just like before, all we need to do is erase all unnecessary lines and apply our final line weights to get that final finish. And there you have it. That's all the construction we're going to be covering today. So just to summarize, first we learn our 1-point cube. Then after that we learn our 2-point cube construction. Then after that we learn our cylinder construction. Then the cone, the sphere, and finally our 3-point cube. Thanks a lot for listening, guys, and I look forward to seeing what you do with these concepts.